or arrows. They seemed to keep on going for quite a way after the push had stopped. By the time the 17th century rolled around, there were quite a few critics of the official version of things. For a start, there was an annoyingly persistent idea that the Earth was not the centre of the universe, that it circled around the sun like everything else. The worst critic of the old ideas was Galileo Galilei, who not only argued with the Aristotelians, he went ahead to prove them wrong. Galileo had a rebellious idea. He thought that facts were more important than theories. So if the facts didn't fit the theory was wrong. Inconvenient facts shouldn't be ignored or explained away. He started to observe and to experiment. He saw that things speed up as they fall. To measure it, however, required split-second timing, and there were no clocks that good in 1602. So Galileo slowed down the rate at which things fell and timed them with a pendulum. He found that big things accelerated at the same rate as small things, and that they all accelerated at the same rate in the same amounts of time. He therefore predicted that if you took away the air, in a vacuum, a feather would fall as fast as a cannonball. He also questioned the idea that things stop moving when you stop pushing them. In fact, he said, they keep going until something else stops them. It's the horse that stops the cart. And how far will a cannonball fly? He now knew that any object begins to accelerate towards the ground the moment it is set free. So the cannonball doesn't fly straight, then stop and fall down. It tries to fly straight, but immediately combines its forward movement with an accelerating fall towards the Earth. So it goes in a curved path that only stops when it finally hits something. This also explained why objects that were dropped when you were moving didn't fall behind you. They always fell straight down alongside, because they kept the movement you had given them to start with. This answered a big objection that a lot of people had to the idea that the Earth went round the sun. They said that if you dropped something, you set it free of the Earth. If the Earth was moving, it wouldn't carry the object along anymore, and so the Earth would move out from under the falling object. But Galileo realised that on a moving Earth, everything shares the same natural continuous movement. If something's dropped, it is certainly set free of the Earth, but it stays moving right along with you, and that means it falls right below where you dropped it. Galileo's ideas on how things moved convinced a lot of people that the Earth could go round the sun without things falling all over the place. More importantly, by explaining how movement could be normal on an Earth travelling through space with all the other objects in heaven, he was hinting that the rules for those other objects might be the same. Heaven, suggested Galileo, worked the same way as Earth. By the middle of the 17th century, most of the right ideas about how things move were around, mixed up with a lot of wrong ones. Isaac Newton used Galileo's ideas and others, like those of Johannes Kepler, to come up with a grand scheme of how things move both on Earth and in space. It's one of the most successful theories ever devised and is still used extensively today. Newton began by thinking that the moon was like a huge cannonball flying through space. Up there, it would have nothing to stop it. So, as Galileo had said, it would keep on going. But it would also be falling towards the Earth at the same time, or more accurately, as Johannes Kepler had suggested, the Earth and the moon attracted each other. that because the Earth was so big compared to the Moon, the Earth would only fall a little way towards the Moon, while the Moon did most of the falling towards the Earth. So why didn't the Moon smash into the Earth? Because the curving path of this huge cannonball is larger than the curve of the Earth's surface. The two curves can never connect. The Moon keeps on missing the sphere of the Earth. It continues flying and falling forever, travelling in an orbit around the Earth. To make this completely clear, Newton calculated the curves. In 1 second, the Moon falls about 2 millimetres towards the Earth and also flies along about 1 kilometre. That makes a shallow curve that carries well outside of the Earth. Newton realised that this also explained how the planets, including the Earth, orbited the Sun. The attraction between them, which he termed gravity, was created by the amount of matter in them, which he termed their mass.
2, 1, 0, all engine running.
That's why a massive object is heavy on Earth. Its large gravitational attraction to the Earth gives it weight. But mass is not weight, despite the fact that the same measuring units are used. On Earth, a 1 kilogram mass weighs 1 kilogram. On the Moon, it weighs 1/6, because the Moon has much less mass to attract it than the Earth. Disconnected from either, that is, in free fall, it weighs nothing. But it's still, of course, 1 kilogram of mass. So, in space, in free fall all the time, how do objects move? If an object in the solar system is not moving compared to the Sun, then the object will fall straight into the Sun. But if it has any sideways movement, it's likely to miss. It falls in faster and faster, swings in close past the Sun, and then flies away. But now it's pulled back and slowing down all the time. Eventually it will end up just the way it started, and the orbit will repeat itself. This is an elliptical orbit.
Main engine start, 3 engines up and burning, 2, 1, liftoff of Space Shuttle Discovery.
Newton also realised that with enough speed, an object might escape the gravity of the Sun, as on Earth an object going fast enough might likewise escape the Earth's gravity and never fall back again.
Discovery speed already 400 miles an hour, altitude 9,000 feet.
All orbits are ellipses. Some are more elongated than others, and one form of an ellipse, where the two foci are together, is a circle. The Earth's orbit is close to a circle, as indeed are most of the other planets. There's nothing in space to resist movement. So the only thing that pulls or pushes on objects in space and so changes their speed and direction is the gravity or the impact of other objects. The most affected are, naturally, smaller objects like comets, asteroids, or spacecraft. A close encounter with a planet may perturb or upset its orbit into a new direction. If the new orbit crosses that of a planet, there's a chance of a collision.
This happens all the time. It was only a couple of days ago that I saw a meteor or a shooting star in the day. This was just a little fragment of an asteroid, maybe the size of a golf ball, and when it hit the atmosphere, it burnt up and we saw all the light from it.
At the Perth Observatory in Western Australia, Dr. James Biggs works on a research project to track the motions of asteroids and comets, and some of these cross the Earth's orbit.
The bigger meteors have a greater chance of getting through the atmosphere, and if they hit the ground, that can have serious consequences. For example, In Western Australia, we have a large crater that's the result of an impact 300,000 years ago of an object only 50 metres across, the size of a rather large truck. But the evidence is still on the ground. It's now a part of a national park. In recent years, in 1908, for example, in Siberia, there was a great event which levelled roughly 1,000 square kilometres of forest, which again we assume was the breakup in the atmosphere of an asteroid or a comet. Not a particularly large one, I might add, only 50 metres in diameter. One of our research projects is to track the positions of asteroids and comets. The aim of this is to determine their orbits, and what is of particular interest is if there are any of these orbits that would cross the path of the Earth. This is an image of an asteroid that was acquired by my research student Hui Lim. During the exposure, the asteroid moved against the background stars. Many groups are tracking such objects, but so far we have found none that is on a definite collision course with Earth.
What could be done if an object was found on a collision course with Earth? An interesting question. Maybe we could evacuate the impact area or send up rockets to deflect it. But first, every part of the sky must be scanned systematically to find any objects that we haven't seen before. In the Southern Hemisphere, Perth Observatory is the only place doing this using the necessary, accurate, computer-controlled telescope.
Australia's position on the globe gives us access to parts of the sky that you just can't see in the Northern Hemisphere. Now, while most of the asteroids are safely orbiting in the asteroid belt, some get knocked out of their orbits and they can come close to the Earth from any direction. This project is important because there's serious consequences if there's an impact. For example, a 10-metre wide asteroid is not particularly large. If it crashed into the Earth, it wouldn't knock the Earth out of its orbit, but the impact energy would be the equivalent of a nuclear weapon such as those used in World War II.
So, the Near-Earth Object Program is one scientific effort we might not be too pleased to hear from, if they discover something coming. But wouldn't you rather know what's out there? Wouldn't you rather know how things are moving?